look at the overhead here, see what the chapter 7 entails here. We are looking at substitution reactions. Our main substrates will be alkyl halides. So we'll have to look at their structures carefully, define a couple terms here. We'll do the naming, the IUPAC naming of haloalkanes, and we'll combine that with the alkyl alkanes that we learned before. So the names will get a little more complicated there, but the same rules will apply there. We'll look at the properties, including, the structure to determine why they react the way they do. Remember, everything is based on the structures of compounds. We'll take a look at different important halogen compounds. You've probably heard a lot of names of them, Teflon or haldane, DDT even, maybe. We'll examine that bond, the carbon-halogen bond, and think about the orbitals that are present there. The sigma bond should be readily apparent. But there's also the sigma star, and that's the empty orbital. That's actually where the nucleophile will attack. And that will have important consequences for some of the types of halides we'll look at. In particular, the inversion of the stereochemistry. If it's a secondary halide with stereochemistry, that gets inverted, R to S or S to R. And it's because of the attack of the nucleophile on the sigma star. So leaving group, halogens are very good leaving groups in general because what? Their conjugate bases are stable, okay? The X minus is a very stable species because of electronegativity. The conjugate acids are very strong, which means what? The conjugate bases, the X minus, the leaving group part, once it comes off, is very stable and very non-basic, okay? So that's an important consequence there. We'll look at a lot of different nucleophiles, and I think this is a difficult part, keeping track of all these varieties of nucleophiles. They all have some things in common that we'll have to point out, but that means you can make a ton of different products. And so I've kind of warned you here, right? There's a lot of reactions if you consider the great variety of halogens, primary, secondary, tertiary, and then the variety of nucleophiles. So then all the combinations, okay? So it's actually many reactions that we're going to look at. But you've got to unify them and think about the principles and apply those principles, and that will let you keep track of this multitude of reactions. The mechanisms, hopefully, will be clear. We'll use that as a unifying idea. The SN2 versus SN1. And this chapter really boils down to whether it's bimolecular, which is at a primary or a secondary halide, or whether it's unimolecular, a stepwise reaction via carbocation at a tertiary or sometimes a secondary position. So really that primary, secondary, tertiary halide is your first thing to hang your hat on, okay? And whether that's nucleophile is charged or superbasic, that's the next thing to hang your hat on. And if you can keep track of those two factors, then you can keep track of this multitude of combinations that can come up here, okay? Examine the structure and then apply the principles there. There's your friend SN2 that you'll get very familiar with. That'll help you out with the ChemTube quiz question also. And there's your sigma star on the back side of that orbital. There's our nucleophile coming in. And there's a point here where it looks like, oh, that's a pentavalent carbon. No, that's a partial bond to the nucleophile, a partial bond here, okay? So that's not a violation of the octet rule. That's the transition state between starting material and product here. See the X minus coming off and the nucleophile going on. So you're really changing one lone pair on a nucleophile for another lone pair coming off on the halide, which is more stable. Well, the weaker base, right? It's the side that has the more stable minus. So that's a good way to look at it, right? And then you can think about, well, what nucleophile is going to want to go on and why is that a good leaving group? Things to keep track of. Yeah, this is a heavy chapter, right? Look, a 2-page outline there. We'll see some applications. We'll see the biological methylating agent, SAM, S-adenosyl methionine. Then we'll have SN1 with tertiary and secondary and weak nucleophiles or neutral nucleophiles. That's often the difference between nucleophilicity, whether it's charged or not. If it's a charged nucleophile, it's going to be a better, stronger nucleophile. If it's neutral, Well, the amines, though, ammonia and the amines are still very good nucleophiles, even though they're neutral. But usually you can look at a nucleophile and just look at the charge and tell whether it's going to be a good one or not. Secondary, tertiary, especially tertiary, and then a neutral nucleophile, they will just simply ionize the carbocation, and then the nucleophile goes on there. Okay. Hammond posse will link the transition state to whether it's exothermic or endothermic for a step, and that's where I said in chapter 6, sometimes they are connected. Okay. The transition state has the character of the stable intermediate closest to it on the reaction profile. So if you have an endothermic step, or you're going to a higher energy intermediate temporarily, that transition state will reflect the stability of that intermediate. So the carbocation character is borne out in the transition state leading to that carbocation. That's why we need to talk about it for SN1. And that'll be, more familiar. These terms will start to sink in over time. Even if you've read ahead, I know these terms are kind of jumbled together in your head right now. Don't worry about that. I like to show them to you, though, up front. So SN1 versus SN2. Vinyl and aromatic, no, we don't do these types of substitution reactions on those. Then synthesis, here's the variety of compounds you can make there. Okay. So, well, maybe, yeah, okay, let's stay here. I don't want to keep going back and forth. So let's look at the Hall of Fame. Halides, very important class of compounds. We're going to do the naming. You're probably familiar with some of these. And these are very useful materials used all over the place, produced on very large scale, all sorts of applications, everything from drugs, antidepressants, here Prozac, ethyl chloride, the Numsit spray that athletic trainers use all the time. A dye material, a red dye here that it can actually covalently link with the cotton fibers, the cellulose fibers, and make the red material. All the colors you see around you, both in nature and man-made stuff, is all linked to compounds that can absorb in the visible range. Sucralose, anybody know what that application is? That's one of these artificial sweeteners, right? This is chlorinated sucrose. Sucralose, it's a synthetic material, but it's many times sweeter than sucrose, and it's not metabolized the same way as a normal sugar. It's table sugar, so it doesn't have any caloric content. So you can use a tiny amount of it to sweeten materials and then make it better for the diet. I don't know. Antibiotic here, another colored dye material. Thyroxine, anybody know what that compound does? Produced by the thyroid gland to control metabolism in the body. And notice it's an iodine compound, 3 iodides on here. It's actually a variety of these thyroxine halogenated aromatic compounds that are hormone-like in their activity. And then we have, fluoroglucose, a tracer molecule for biological imaging. Epibadidine, a chloropyridine, painkiller compound. Fluorane, which is a replacement for a freon, doesn't damage the ozone hole. Vinyl chloride to make polyvinyl chloride, building material. Isoflurane or haldane, analgesic compound used in the operating room. 2-chlorobutadiene, that's a polymer material used for food preservation. And then if we look at the Hall of Fame, we got to look at the Hall of Shame, right? Now, compounds on their own are not evil. Maybe evil people use them for evil purposes, but here are some bad actors. You could say Freon, one of the great refrigerant compounds, not used for refrigeration anymore because it does damage the ozone hole in the upper atmosphere. But we have a replacement for it now. And this is just, dichlorofluoromethane. Then we have bromomethane, Hall of Shame here. It's a carcinogen. It's also an antifungal compound. If it's overused or misused, that can create all sorts of problems. Chloral, the date rape drug. Yeah, there's an evil drug for you. Mustard agent, the chemical warfare agent from World War I. Nasty stuff. Dioxin, a toxin that comes out of the paper pulping process. That's released in rivers and streams and causes a lot of environmental damage there. Aldrin is a pesticide material. It's been banned. PCC, DDT, PCB, And triclosan was in the hand sanitizers initially as an antibiotic material, but it creates drug-resistant forms of bacteria readily. And hospitals don't want that, okay? So that's been outlawed in most hospitals. It's good at killing bacteria, but it kills off the drug susceptible ones and leaves the resistant ones available there. So I don't know, a problem. Leaving groups. So we'll look at these. There's the halogens, also an ammonium ion. We'll have to get back to that. But first, let's go over here and do some naming and look at the general reaction here. So here's what we're talking about. And we have to examine this carbon carefully and know whether it's primary, secondary, or tertiary, right? As I've drawn it now, it's kind of generic. These lines, might be hydrogens or other carbons now, but we need to examine that and know which one we're talking about. And notice at first here we're talking about what? sp3. And that's really the key. The hybridization has to be sp3. sp2, we'll see, or sp hybridized halides, and we can have those as well. Those are not reactive under SN2 and SN1 conditions, okay? And then here's our nucleophile, and that's got to get on there. Our leaving group's going to come off with this pair of electrons. The nucleophile's going to get on there, and there's what we're going to make. The leaving group usually will come off as a charged species, and that stability, the pKa, that conjugate acid, we can look at that to get an idea of why this reaction might work. So here's a variety of ones here. We should be familiar with these names. If the halide or some sort of X group, non-carbon group, is directly on an alkene, notice that's what? That's sp2. Hybridization, that will not react under the conditions we're talking about in this chapter, okay? And that's just a simple change of hybridization, right? That has more S character now. That's a stronger bond. It's going to be harder to break. And besides, in the bimolecular action, this backside attack is hindered because all these atoms are held in the plane. So no reactivity for this one. This also has a common term, vinyl, okay? Polyvinyl chloride, you've probably heard before, vinyl halide, whatever. Know that common term. If a group's directly on an alkene, that's called a vinyl group, okay? But this is not vinyl, and this is not sp2. Here's an sp3 group, right? And this has a different name. This is allylic. And that's a very good leaving group, both for SN2 and for SN1. And you can already see maybe why. If these electrons come off, you have a cation here, and that's resonance stabilized, okay? So examining the halide and the structure of the halide is a key factor moving forward. But keeping those terms straight. And then this one here, directly on a benzene, again, that's still sp2. That's not going to be good for SN2 reaction or SN1. Okay, those intermediates are not stable directly on the benzene like that. This is called a phenyl group, okay? Phenyl, okay? pH, or sometimes it's abbreviated little p and h, okay? And that's a group directly on a benzene. But now if we move the benzene over and have what? An sp3 hybridized extra methyl group here, okay? It's not called phenyl anymore. This is benzyl. And this is very good for SN2 and SN1 reactions, okay? You can already kind of see what the intermediates will look like. Here we'd have the plus charge right on the side of the benzene in an sp2 orbital. That wouldn't be good. It's not conjugated to these pi electrons that are perpendicular to it. But right here, if we ionize and have a cation, then we can have resonance stabilization off the benzyl position. So keep that straight. I've used these terms quite a bit and discussed it with a couple people, keeping them straight. But here we define them clearly and show you the structures and then moving forward there. Okay, questions on that? All right, let's get into naming. Naming halides, IUPAC naming. And our key here is we're going to name these halo, alkyl, alkane. Okay, so there's our parent, right? The last one there, the suffix part. Alkane, that's our longest chain. And then whatever we have here, X and then Y, these refer to what? The position on the alkane where those groups are. And we're going to alphabetize them all together. We jumble them all together. We give the lowest possible numbering sequence, the point of first difference. And then when we alphabetize, we mix in the halos with the alkyls, okay? So what are the halos we're talking about? We're talking about fluorine, so that becomes fluoro, okay? Chlorine, that becomes chloro, and bromo and iodo. The O terms are like the YL terms for the prefix for the alkyls, okay? So let's see some names here. Let's get into this. So what's this? Start very easy. 8 in the morning on a Monday. We ought to be able to do that one. Okay. So what's our parent here? Butane. Very good. And at what position do we have what? At the one position we have what? Bromo. Now, do we need that one? Yeah, because is there a 2-bromo? Yes, there is. And is that a different compound? It sure is. Okay. That would be 2-bromo. Okay. And notice the difference. That's why we're talking about nomenclature, not to torment you with another system of rules, but these are going to react differently. 1-bromobutane is a primary halide, right? Whereas the 2-bromo is what? Secondary. That's going to have different reactivity. Is there a 3-bromobutane? Maybe that question's a little tough for Monday morning, but some people are right on it. Why is there no 3-bromobutane? Somebody was shaking their head. Yeah, it's the same as 2. And that's the other rule. Give it the lowest possible numbering. And there's no such thing as 4-bromobutane, okay? That's an incorrect name. So make sure, you keep the basics down there. And let's combine this maybe with stereochemistry. So there's a chloro what? 1, 2, 3, 4, 5, 6 hexane. And at what position is it? 3. Okay, so 3-chloro hexane. Are we done? Oh, I've drawn that bold. So what is it? Is this a stereocenter? Yeah, we got to remind ourselves of that. And what type of halogen is it? It's secondary. Okay, and is it R or S? That needs to be part of the name. Let's see, top priority is chloro, and then what? We have a propyl ethyl here. So 2, 3. We've already got 4 in the back. So what is this? 1, 2, 3. Is that clockwise or counterclockwise? Counterclockwise, so indeed it is what? S. So that's part of the name. Those S's and R's have to be in the front. And if there's only one, you don't have to number it. But if there's multiple R's and S's, then you have to have numbers in front of each one, starting with the lowest one. Okay. How about this one? Yeah, now we got halides and alkyls mixed in all over the place, don't we? So what is this? Looks like an isopropyl something. No, number down the whole thing. 1, 3, 4, 5, 6, 7, 8. Yeah, so what is it? An octane, I think. And, it's good form to circle that whole parent there. And then the substituents really stand out, I think. So we've got 3 methyls, so trimethyl and a fluoro. So what do we do? First thing we got to do is number it, right? The lowest possible numbering, starting from the end. So 1, 2, 3, 4, 5, 6. Does that look right? If we started over here, it'd be a 3, and that would be wrong. It'd be too high compared to the 2 side. So alphabetizing now. Which comes first in the alphabet? Fluoro. So it's 5-fluoro. And we don't have any stereochemistry shown, so we don't have to worry about it. Okay, they're all just standard lines. And then we've got what? 2, 3, 2, 3, 6 trimethyl. Sorry, that's kind of small. 5-fluoro, 2, 3, 6 trimethyl octane. Everybody okay with that one? Maybe just one more for the fun of it here. How about a cyclic one? And let's have some stereochemistry here. We've got a cyclopentane. We can at least see that part of it. We've got an ethyl. and then iodo. So just start with the parent, right? Cyclopentane. And we don't need to circle that, but numbering now. Let's see. So one of these would be 1. One will be 2, right? You wouldn't want to start down here with 1, because then you'd have 1, 2, 3, 4. So 1, 2, 3, 1, 2, 4 will be our thing. So we have iodo versus isopropyl. So which one is going to be first in the alphabet? That's how we break the tie here, right? Between all the halogens and alkyls. So does iodo come first in the alphabet or isopropyl? Do we alphabetize by the I or the P in isopropyl? It's by the I, right? Iso, so it's I-S. Iodo's I-O. So which one's going to be number 1? Iodo, yeah. So 1, 2, 3, 4. Okay. You could say, well, wait a minute, ethyl comes first in the alphabet, doesn't it? Well, no, that's the wrong numbering position. Okay. So we use the alphabet for a couple things here. Determine the priority of which gets the lowest number, lowest overall numbering, and then alphabetizing here. So what would it be? What do we got now? 1 iodo, 2 isopropyl. No. Okay. So up here we have to have 4 ethyl, right? So that's first. Then 2 iodo, then 2 isopropyl. Okay. So yeah, so we do alphabetize when we string the prefixes together, but we use the alphabet to determine which one got the lowest number. Does that make sense? And so we apply those rules sequentially. Are we done with this problem? Hopefully. No? What do we need to do? R and S now, right? So let's see. This stereocenter right here, R or S, let's see. Top priority would be iodide, obviously. And then methine versus methylene. We go over here. Oh, it's already got a 2 on it. Very good. And then 3 here. So 1, 2, 3. Hydrogen's already in the back. So what's that? So 1S. So this will be in the front there. And then we've got this one here. That one might be a little trickier. Good. Hydrogen's already in the back. And then we've got methine, methylene. So it's between these 2 methynes. But this one, you see, has an iodine on it. So that would be 1, I think. Oh, it's already got a 1 on it. Good. And then this one here, methine versus methylene. So that's also S. Okay. And then we've got 4 down here. And this one, the hydrogen's in the front, so we have to put our eyeball back here, right? And look, yeah, from that backside. And then methylene. But this is next to a methyl, so this will be our 3rd priority one, right? And so what gets higher priority here? This methylene over to methine. Oh, and then the iodide, yep, is over this one here. So I'd say this is 1, 2, and then if we pull it out, again, holding the hydrogen in the back. So is that's clockwise, right? So I think that's R. So yeah, you need this whole thing in the front, and then 4 ethyl, 1 iodo, 2 isopropyl cyclopentane. That's a tougher problem, okay? But I think if you apply the rules sequentially, you'll be okay on that. All right, let's look at a couple other common names here. Chemists often use these common names for halides. So what would you call this? 2-chloropropane. That's easy with the IUPAC. It's also just called isopropyl chloride. And these chloride or halide names end in IDE, and you're probably more familiar with those. Ethyl bromide, ethyl chloride, ethyl fluoride, methyl bromide. I've used those terms before, but when in doubt, you can always use the IUPAC name there. How about this one? Tert-butyl fluoride. Tert-butyl fluoride because it is a tert-butyl group bonded to a fluoride. What would be the IUPAC name for that? Sometimes that's good to review. What's the longest chain here? Propane, right? And again, circle your parent. That's the longest chain, right? So if you do it systematically here, yeah, you got to call it that. And then what is it? It's 2-fluoro, 2-methyl. And that's a mouthful. 2-fluoro, 2-methylpropane. Ouch. We just call that tert-butyl fluoride. Okay. I think that's a little more common. And then here's your Nemsit spray. Ethyl chloride. That's an easy one. And how about this one? Methylene chloride or dichloromethane. Okay. Methylene chloride kind of combines that name of what it is. This is a very important solvent for the semiconductor industry, the computer industry, to clean different computer components. It's a very good degreaser. Gets rid of all traces of grease and keeps things very clean for conducting. And then we've got a couple others here. How about chloroform? Another very important solvent. And one of the old analgesia agents, okay, along with ethyl ether, diethyl ether. They're not used anymore for analgesia. This one's too toxic, and ether is too flammable, causes too many bad situations in the hospital. But chloroform's just too toxic. But it was used initially to knock people out for operations. And then carbon tetrachloride kind of rounds out all of those to talk about. Yeah, we already showed you a few of those. Let's start to examine the structure and think about how these things react. So when you look at a halogen, what's the first thing to notice here? So it's carbon bonded, to a big atom, you could say. Fluorine's pretty small, though, but chlorine and bromide, and those will really be the workhorses. Chlorine and bromide are the very good leaving groups. Fluoride, you could say, well, that should be even better. It's even more electronegative. The problem is it's smaller, and a carbon-fluorine bond's too strong. And it turns out that there's other factors there that make that a very bad leaving group. Okay, and plus the conjugate acid is not that strong. HCl, HBr are much stronger acids than HF. Okay, and so you might say, well, what about iodide? How come we're not emphasizing iodide? Well, that's a weaker bond. Those compounds are less stable from a practical point of view. Carbon iodides are just too difficult to deal with. They don't store very well. They don't have a good shelf life. So it's too weak of a bond. Okay. But we will use iodides periodically there. As long as you use it right away, it can be a good thing. But certainly not fluorides because they're just too darn stable. Okay. And it turns out it's not a very good leaving group. Well, what is it about the bond? Well, look at the bond dipole moment, right? It's polarized already toward the halogen. So this is the partial negative end there, and carbon's the partial positive end. And that's attractive to what? The nucleophile. The reagent is electron rich. So we say the halogen is electron poor, okay? Or it's electrophilic. Okay? And I've used that term before, but what is electrophilic? It's that carbon bearing the halogen, okay? And then when we talk about the reagent, we're talking about a pair of electrons. And no, we're already abbreviating NU. What's the NU stand for? Nucleophile, right? It wants a nucleus. Well, where's the nucleus it wants? It's right there, the carbon, right? That's the partially positive end. So you can already see how these things are going to work reactivity-wise. Let's look at a little bit on the properties here and put a couple halogens in context here. Ethyl bromide, ethyl chloride, ethyl alcohol, and ethane. Okay, so there we got hydrogen, a couple halogens, and then an alcohol. Let's look at boiling points. And minus 89 degrees C. So clearly at room temperature, ethane is a gas. Okay, very weak intermolecular forces. But we've just been talking about this polar covalent bond, right? The electrons polarize there. So we have a permanent dipole moment now. And it's a much heavier atom, obviously. So what's that going to do to the boiling point? It should go way up, right? Stronger intermolecular forces. Yeah, it's almost a liquid at room temperature, but it is a gas. It can be easily pressurized in one of those Numsit spray bottles. When it comes out, it cools the surface of the skin and dulls the pain a little bit. So Numsit spray, but yeah, when it comes out, hits the skin, can easily evaporate. And as it evaporates, that's that cooling sensation on the skin too. So something about the properties. What about bromide, ethyl bromide? What's that going to do to the boiling point? Well, I'm already drawing them left to right here, so you can already tell, right? Much heavier atom, bromine, right? Yeah, and still a polar covalent bond. Not as electropositive, because it's not as electronegative as chloride, okay? But they're both primary, whatever. So what about the boiling point? That's what we're talking about here. Oh, 39. So degrees C. So clearly at room temperature, which is what, about 23 degrees C, that's indeed a liquid, okay? Because it's heavier. It's compared to ethyl alcohol. Now, an OH, you know, if you look at the atomic mass here, what's that? 16 and one more 17 versus bromine, which is 80, right? 80 AMU grams per mole. Much heavier, right? But what happens here to the boiling point? Up or down? Well, I'm drawing it left to right, so you already know. What is it, 80 degrees? And that's amazing, isn't it? Because it's lighter. It's much lighter. Yeah, you have a polar covalent bond here, just like these others, but why is it so high? And it really jumps up dramatically. What is it? Intermolecular forces? What's the special intermolecular force now that the halogens don't have? That's why I'm emphasizing this. What? H bonding, right. So if you've got a hydrogen on a small electronegative atom, which the halogens don't have, you know, they're very electronegative, but these hydrogens are on carbons here, so no H bonding. And you see that borne out in the properties, okay? Much higher boiling, even though it's lighter, okay? So ethanol is higher that way. So halogens, yeah, generally have very low boiling points, similar to alkanes there. Okay, let's go into the overall reactivity factors. And I like to give you the whole story here in summary form. So here we've got, well, let's just make this primary right now. So we've got one here. And we're going to do a reaction with our nucleophile. And if this guy's charged, and if it's primary, yeah, we're going to do that type of reaction, and we're going to call this SN2. And because the rate limiting step is just this one collision between the charged nucleophile and the unhindered leaving group, primary, secondary, it's going to be bimolecular like that. And the rate will depend upon some rate constant times that starting material concentration times the concentration of the nucleophile, okay? And that's typical SN2 reactivity. Now, generally that will be the same for secondary, as long as this is a small, charged, weak base nucleophile. And this has to be charged or an amine or ammonia can also do these type of SN2 reactions. Okay, if it's tertiary or secondary in some cases, depends on the stability. Actually, primary can go this route that I'm going to show you now. If the intermediate cation is stabilized by resonance, and instead of being charged, the nucleophile here, it's going to be neutral. Okay, so once we have a negative charge here, here we have neutral, and we have a more substituted tertiary and secondary. So our reactivity here is going to be unimolecular. Our slow step is just going to be that, the ionization. The solvent's going to play an important role. It's going to have to be a polar enough solvent to stabilize that carbocation intermediate. Okay. Notice this only involves the decomposition of the more hindered, the more substituted halide. So the first thing to look at is the structure of the halide. The next thing to look at is the charge state of your nucleophile. And yeah, there'll be some solvent considerations as well, okay? But this is what? Leading to the same thing, really. Eventually that gets on there. And, you could say, well, who cares, Dr. Andrus? It eventually got to the same thing. Well, the mechanism is different, okay? And we call this one SN1 now, and the rate will only depend upon the concentration of the starting material. It's independent of the concentration of the nucleophile. You can dump in all the nucleophile you want. In fact, a lot of times the nucleophile in these cases is the solvent. We'll call these solvolysis reactions then, either in water or methanol or ethanol. We'll make ethers, but very different mechanism, different rates. Carbocation, stereochemistry will be different too. Okay. With SN2 here, if it's got RRS stereochemistry being secondary, it cleanly inverts. Okay, which is another hallmark of SN2. But that's the whole shebang for chapter 7 right there. I could stop right there and just have you take the test, right? No, we'll look at the details, don't worry. But there's another one here. Tertiary or secondary, in particular, or sometimes primary, depending on the conditions. But let's look at the one where indeed it is tertiary. And we're going to look at this one here, where we've got a charged reagent, and we're going to call it a base. It's a strong base. The pKa of its conjugate acid is very high, okay? Or it's hindered. T-butoxide is going to be the main one here. In fact, I'm just going to draw this reagent for you, because that's the key strong base hindered thing that's not going to be a good nucleophile because of its size. T-butoxide with a tert-butyl O-, that alkoxide is not going to do substitution. It can't get here and hit the back of this sigma star orbital. It just grabs a proton, which is a lot easier to do sterically. And look at that mechanism. It's still bimolecular. The two are colliding there, but it gives a different product. It gives the alkene product plus the protonated alcohol. We call that not SN2 or SN1. That's not a substitution. That's what type of reaction? That's a question or? Sure. Base. Yeah, strong base. So we're not calling this substitution here. What are we calling it? Remember there are 3 types of reactions. Which one is this? Elimination. We're still taking off the leaving group, and indeed it is leaving, but look, it's deprotonating at the same time, and then flowing the electrons this way and giving it elimination. Call this E2, elimination bimolecular. Okay. Has similar kinetics to SN2. The rate is bimolecular. Depends on the concentration of the base, but because it's hindered and hindered here, okay, the substitution can go. That's the bottom line of chapter 8. So we've got everything we need now to take test 2. Should we just take test 2 and get it over with? No, we'll do the details of the chapter, don't worry. Okay. So yeah, let's look at some examples here of good SN2 reactions. And you'll get a feel for this. We'll define clearly, what's a good leaving group and what is a good nucleophile, okay? We already got a little feel for it, I think. How about this one? So chloromethane plus sodium hydroxide going to methyl alcohol plus sodium chloride. Oop, not iodide, chloride. Okay. Looking at that reaction, can you identify what the leaving group is and what the nucleophile is and the type of leaving group it is and whether or not this reaction might be useful? So there's a few things we can ask here. Can we figure this out? Where's our leaving group? Well, obviously right there. Okay, chloride. And what type of leaving group is it? Primary or methyl? It's the smallest leaving group you can have, actually, okay? And then where's our nucleophile? Well, sodium's what? Sodium hydroxide. Here is an ionic salt. So the charge is what? Plus on sodium. So where's our nucleophile? Oh, there it is right there. Okay. And is it charged? Yeah, okay. Very charged, right? Pretty strong base. The pKa of water is what? 15? So that's a little on the high side, actually. We don't like that too much. That's kind of bordering on a strong base, which it might do some E2 elimination. But here we don't have any hydrogens on a carbon attached. To do the E2, you have to have another carbon with hydrogens attached there. So yeah, so this reaction just goes like that. And here's our product. Here's where the nucleophile's on there. This is methyl alcohol. And there's the byproduct, sodium chloride, that we're not really worried about that. But, you know, the variations, we've got all sorts of nucleophiles we can talk about now with different methyl leaving groups. The mechanism, which we'll get to later, will be just that. This is indeed an SN2 reaction for substitution, nucleophilic bimolecular, okay? The collision of both the substrate and the reagent is borne out in the rate expression, okay? Here's another one. How about this iodide plus sodium sulfide going to what? Okay. Now maybe we'll throw in the idea of, well, what's the product? Okay. So you already see the primary iodide, okay? And, you know, that's electronegative also. That's partially positive, right? Sodium, yeah, the metal's always positive charge. Sulfide, HS on the sulfur will be the negative part there. And remind yourself what that looks like Lewis dot-wise. Right? 6 valence electrons for sulfur, negative charge, so it's got 3 lone pairs, and it's charged. So that's a very good nucleophile, right? So just kind of see what could that do. That is primary, so that's good. And so what would be our product? The essence of skunk. Oh boy. Really glad we could make that material. Yeah, you'd really have to control that because it's pretty volatile and would have a very significant odor. You'd have to have some control capabilities at your plant if you were making it. The neighbors would not be happy with this reaction. Okay. But you can see there's our nucleophile going on. And yeah, the leaving group here. So we're exchanging S minus for I minus, really. Okay. And you can see that would be a favorable thing. I minus, that comes from a very strong acid from HI, which has a pKa of minus 10. So the conjugate base there is very stabilized and very unreactive. Okay, how about this one? Methyl bromide plus potassium methoxide going to what? So variations here, right? Here we got primary. Here we got KOMe. So we'd want to think about it that way. And what would be our product? The ethyl group would still be there. And then the O, and then what? That CH3 from the methyl alkoxide. Sometimes I draw methyl, sometimes I draw it all out. You should, be okay with that. Same thing with ethyl, but that's the 2-carbon thing. This is methyl, so this is a methyl ether, okay? And what's our byproduct here? Potassium bromide, okay? So that should be a little bit okay. What other things can be nucleophiles? We'll need to get into that and what can be leaving groups. So, halides are very good leaving groups because what? The X minus when it comes off is very stabilized. But there are other things that can be good leaving groups, not alcohols, okay? Because that conjugate base would be hydroxide coming off. But if we protonate it first, okay, and have hydronium ion, that comes off as water. So that actually turns out to be a very good leaving group, okay? And we can have sulfates. We'll see some of those as well, the so-called tosylate leaving group, okay, where the conjugate base, the O minus, coming off as resonance stabilized. So it's not just halides. We'll add in a couple other ones too. Let's do a couple more here. Got some time. How about amines? How about this? Plus trimethylamine. And how about same one but just with ammonia? And how about the same one but with pyridine couple different amines. These are all neutral. Oh, let's add in another charged one. How about potassium thioacetate? Kind of have to examine that one and figure it out. Well, let's see. Here's our leaving group again. Here's our nucleophile. We have to add in the lone pairs, right? Oh, and the negative charge there on the sulfur. So the amines, the ammonias, are neutral, right? But they're on an atom here that's not very electronegative. On the Pauling scale, what's nitrogen? It's not as high as oxygen, right? It's to the left of oxygen there. It's right next to carbon. Carbon's what, 2.4? Very moderate. Nitrogens are 2.8, which means a lone pair on nitrogen is very available for bonding. So I'm drawing this to scale now. That lone pair is very big. sp3 hybridized means it's going to be available, right? So let's go ahead and use it as a nucleophile, even though it's neutral. And what's it going to give? Well, that propyl group will be there, and then the 3 methyl groups will be there. What's the charge now, though, on this nitrogen, if it functions as a nucleophile in this reaction? Do the formal charge calculation. You see how these principles, it's +1, right? Yeah. And then what happened to the bromide? Oh, there it is. It generates a salt on its own, okay? So that's a tetraalkyl ammonium bromide product, okay? Propyl trimethyl ammonium bromide. But you can see, because that's a nucleophile, that would be our product. Same thing with the ammonia. We'd have the 3 hydrogens on there. If you have excess ammonia here, because you have hydrogens on here that can come off, remember the pKa. What's the pKa of an ammonium cation if you've got hydrogens on there? That's one of those you need to know. pKa of ammonium cation, what is it? 9, very good. So you can use excess, you see, of the base, add in that, and then you'll get what? The neutral amine product, okay? So that's a way to make amines using SN2 reaction. Pyridine, this lone pair here, again, I'm drawing it to scale. Why am I drawing that lone pair smaller now on pyridine? Because they're held closer, right? Higher S character. So it's not as reactive as simple amines, alkyl amines. But these aromatic amines can also be nucleophiles. And yeah, what would this look like? It'd have the pyridinium group there. And yeah, that would be positively charged. Yeah, that's right there. 1, 2. Yeah, I got it. Okay, that'd be the pyridinium bromide product. Okay. Wouldn't react as quickly as the ammonia or the amines there, but that'd be good. Okay, what about this one? We have another sulfur nucleophile. And you might be tempted to think, well, we could resonate that and have the oxygen be the nucleophile. But then we'd have to have a carbon-sulfur double bond, and those aren't very good. The pi bonds between 2 atoms that are very different sizes that way. So actually the sulfur stays as the nucleophile. So that's a question to ask there for that one. And so what do we get? We get the propyl thioacetate. This is called a thioester. That's a functional group we haven't seen before. But just applying the principles, there's our charged nucleophile, right? Primary leaving group, yeah, that'd be a good SN2 reaction, actually. Okay. Yeah, and we're over time already. Sorry about that. So we'll keep practicing. We'll define carefully what are the characteristics of good leaving groups, although you've already got a feel for it, right? Conjugate base is very stable, very happy being an anion, so that makes those good leaving groups. And then the characteristic of good nucleophile, small and charged, okay, not very hindered. You already saw the example of TB toxide switching over and doing the elimination. So we'll have to examine the details of the mechanism, the SN2, the attack of the sigma star next time. And that'll be the key thing. So very good. We'll see you next time. Thank you.